All right, welcome. In this video, I'm going to go over our midterm here for 2021. There's two data points that you all are going to collect for the midterm. The first is going to be the time airborne, and that we'll call that capital T. All right, so how long is the payload, the tennis ball, in the air? We'll call that capital T. That's going to be measured in seconds. At the same time, or during the same launch, you're also going to record the launch angle. Okay, and so that's going to be an angle theta that's going to be measured in degrees. As a quick reminder, we're going to have a science team stationed 30 meters away from the launch pad. That launch pad is going to fire our payload, a tennis ball, up into the air, where the science team will be able to keep eyes on it and use an altimeter to measure this angle theta right there. So the time airborne and the launch angle will be two pieces of data that are collected in order to reach a couple conclusions. So the first conclusion that we want to reach is the initial velocity. In order to calculate initial velocity, like how fast do we have to launch something so that way it's reached a stop by, half of this time later. The time airborne is the time up and down, but we really only care about the time to max height. And so one of the things that we'll need to do is divide T by 2 to get the time to max height. The time to max height we'll call lowercase t. And so that's really the time that we're going to plug into our equations. To calculate initial velocity, we're mindful that gravity, 9.81 meters per second squared, is the acceleration due to gravity that's slowing it down. So the initial velocity is actually just going to be the product of that acceleration times that time. It comes from this general equation of motion, equals u plus at, where the final speed will be 0. So the initial speed is sort of some value that's equal to the product of gravity, 9.8, times this time, right? So it's like gravity opposes this velocity, so we're launching something up with positive velocity, so gravity is negative compared to it. So it's like whatever the value of this term is, that's the negative of the initial velocity, because we know gravity brought it to a stop at the top of its flight. Like no one's going to launch anything so fast that it's going to go into orbit or leave Earth's gravity field. Earth is going to slow it down to a stop, right? It's the speed of 0. And so we can calculate how fast it must have been going because we know this time. We know how much time it took gravity to slow it down. Remember, which is half of the time airborne. So the initial velocity is just 9.8 times this value t right here. That's all you have to do to calculate that. That's the initial velocity. So that's one conclusion you're going to reach. Conclusion number 1, the initial velocity, it's just calculated as 9.8 t. That's going to give you the velocity in meters per second because 9.8 is meters per second squared. So we multiply it by seconds, that cancels out. We get a velocity. Also, report it in miles per hour. And the way to calculate that is just to multiply your initial velocity by 2.23. Then it turns it into miles per hour. Okay, so that's conclusion 1. Pause the video now and rewind it if you still need to look at this for a moment or two longer. I'm going to move on to the next conclusion. I still want to keep some of this stuff up here though, so let's go on to conclusion number 2, which is going to be the height based on this time data. The height of the rocket is just going to be 1/2 g, this, this acceleration due to gravity, same number, 9.8, times that time squared. All right, so the same lowercase t that you calculate here, square it, times it by 9.8, and then divide it by 2, or times it by 1/2, and that'll be the height. That's also going to be in meters. And then you can multiply that by 3.28, and it will turn it into feet. There's 3.28 feet per meter, so meters cancels out, will be in feet. So report your height both in meters and in feet. And then lastly, we're going to calculate the height based on this data, the launch angle, And because we're going to know the side adjacent to our launch angle, and we know the launch angle, we're interested in the side opposite from it. So the height here is just going to be the tangent of theta, which remember relates the opposite to the adjacent, times the adjacent, and we're going to be 30 meters away. So like we're going to measure this distance out. So the launch pad is always 30 meters away from our science team. Our science team will measure these angles theta. If you're an e-learner, we will have a dedicated launch for you, and the in-person students will help to sort of collect your data, but you'll also be able to sort of, time it, because you'll have eyes, have the computer out there, so you'll have eyes, a camera on the payload for yourself, so you can also collect your own data. It'll just be difficult maybe to collect this launch angle data. So the height is also calculated just as the tangent of that angle theta times 30 meters, and because meters go in, meters come out, and we also want to remind ourselves that there's 3.28 feet per meter so that we can convert into feet. All right, so that's conclusions number 2 and number 3. Conclusions number 2 and 3 are really the same answer, the height, just different ways of calculating it, different ways to arrive at that conclusion. If these answers agree with each other, it builds our confidence that it's sort of on the right track for the height. Anytime that we can independently arrive at the same conclusion with an entirely different method, it builds our confidence when those answers agree. Good luck on the midterm.